Good morning, everybody. Am I audible? Okay. Now, in today's class, we'll start off with the fresh chapter of physical pharmaceutics, that is complexation and protein binding. We'll start off with the new chapter. Here, this is a very interesting chapter where you come across a very new concept in treatment of the drug. That is, till now we just studied about drug, formulating it in the form of tablets or the different dosage forms. But here in today's class or in today's chapter, what you're going to study is how we are changing the properties of a drug, how we are treating a drug so that its properties improve. Getting my point? So, now first of all, we have to know or we have to study what do you mean by the term complex. See, here I have sent two PDFs. The textbook, that is Manavalan, I find it actually very simple and easy for you to understand the basics or the introduction part of complexation. So those definitions I'm going to refer from this textbook, that is Manavalan. Here the term complex can be defined as a species which is formed by the association means clubbing of two or more interactant molecules or ions. That is, when you take two or more interactants or the molecules or the ions, and when they club together, they form a species which we call it as complex. Now, such an association takes place because one of the interactants. Now, your question would be, why do they interact, or what makes them interact? And here the answer is that is because one of the interactants, for example, A and B. Now here one of the interactant, it has a tendency to accept a pair of electrons from the another interactant. Now there are two interactants. One interactant will give away its pair of electrons, and the second interactant, it has a tendency to accept a pair of electrons. So this interaction between them, this association between them will lead to the formation of a new substance or a new species which we call it as complex. Now, because of their interaction, as a result, a bond is formed between the two interactants. A bond will be formed between the two interactants, that is the substrate and ligand. And the compound thus formed, we call it as the complex. So, in pictorial representation, if I have to present, it is nothing but there is a substrate and there is ligand. Ligand will donate its pair of electrons to this substrate, and these two will interact to form a substance which we call it as complex. So, complex may be defined as a species which is formed by the association of two or more interactant molecules or ions. Such an association takes place because one of the interactants, which we call it as a substrate, it accepts a pair of electrons which is donated by the other interactant, which we call it as the ligand. As a result, there will be a bond which will be formed between these two interactants, that is the substrate and the ligand, and the complex thus formed, we call it as the complex. The substance thus formed, we call it as complex. Okay. Now, the same thing when I'm going to represent it in the form of an equation. As I told you, here complex may be considered as a species of definite substrate to ligand stoichiometry. There is substrate and ligand stoichiometry which can be formed in an equilibrium process and they exist in the solid state. So here if I consider Ms plus Nl, the term M indicates the number of substrate molecules. How many substrate molecules are present to accept the pair of electrons? And Nl, N stands for the number of ligands. And how many number of ligands are there to give away the pair of electrons to these substrate molecules. That will give you the complex. This Sm and Ln indicates complex. That is, it is a species formed by the association of substrate and the ligand. M molecules of substrate, N molecules of ligand interact together where there will be a bond which is formed between these two interacts. And the interaction between them is accepting a pair of electrons from the ligand by the substrate. This leads to the formation of complex. Is this thing clear? So this is nothing but the basic definition of complex. If you understand this definition, then throughout the chapter it will be very easy for you to understand the rest of the explanation. Now, I told you in the very first sentence, or I told you in the beginning that we require this kind of complexation because it has the ability to change some of the properties of the constituents. That is, some of the properties of the complex, it will have the changed properties. Now, the properties which are altered, they are like, what are the properties which will change? See, the ligand and the substrate will have their own physicochemical properties, but when they club together to form this complex, there will be change in the individual properties of these substances. There may be change in properties such as solubility, or there may be change in the properties such as light absorption. Light absorption changes, conductance changes, the partitioning behavior changes, and the chemical reactivity changes. So, solubility, light absorption, conductance, partitioning behavior, and chemical reactivity. These are some of the properties which will change when we form a complex of the drugs. So the drug will have some other physical property when it is kept all alone. But when the drug interacts with some other substance to form a complex, so the complex will be having the altered properties. Okay. So that is about the basic changes or the alterations that you can find in the drug molecules. So coming to the next topic, that is types of complexes. Now there are two main types or groups of complexes. There are two major types of complexes. The very first one is the metal ion coordination complexes. Metal ion coordination complexes. Just a second. So here I was telling about the different types of complexes, and there are basically two different types of complexes. The first one is metal ion coordination complexes, and the second one is the organic molecular complexes. These two complexes, or these are the two different types of complexes where they have their own way of interaction. Okay. Based upon the molecules which are involved and based on the type of their interaction, the complexes are classified for. Now, in brief, if I have to tell you what the metal-ion coordination complexes consists of, or why they have this name. Okay. Here, the metal-ion coordination complexes, one interactant always is a metal ion. It always consists of a metal ion as one of the interactant molecule, whereas the other interactant molecule, it may be inorganic or organic molecule or some ion. Okay. And always this organic or inorganic molecule, that will be the ligand, whereas this metal ion, that will be the substrate in this type of complex. Metal ion is the substrate and the interactant is the organic or inorganic molecule. And here they are formed by the transfer of a pair of electrons. So definitely there will be transfer of pair of electrons from the ligand to this metal ion. That is, there will be transfer of pair of electrons from the ligand, that is organic or inorganic molecule or the ion, to the metal ion, that is your substrate. And here the bond formed will be the coordinate bond. That's the reason we call it as metal ion coordination complexes. The bond which will be formed between the substrate and the ligand in this type is the coordinate bond. And that is the reason it has the title metal ion coordination complexes. Therefore, the complexes may be considered as a products of Lewis acid-base reactions. If I have to go in a little more details of it, it is nothing but the metal ion coordination complex. It consists of a central metal ion. Here you can see M, that is it, at the center it consists of a metal ion, and it is bonded by an electron pair from the donor, that is the ligand, depending upon its valency or depending upon its uh, what is that, vacant spaces or the vacancy to accept the pair of electrons, there will be ligand molecules attached to it. That is, they are bonded to an electron pair donor, that is the ligand. And usually here the ligand may be a base such as ammonia or an ion such as chlorine, or it may be even an aromatic compound such as benzene, toluene, etc. And here the metal ion coordination complexes, usually they may be neutral or they may be charged. So overall what you study is it consists of a metal ion surrounded by the or bonded by the pair of electrons from the ligand, that is the donor. Your metal ion is the receiver or it is the acceptor, donor acceptor. And the bond formed is nothing but the coordinate bond. Okay. So that is about the Midline coordination complexes. And here another important topic is the number of bonds between the metal ion and the ligand, that we call it as the coordination number. Coordination number means the bonds. Like for example, there I showed that M is surrounded by 4. It means its coordination number is 4. So the number of bonds between the metal ion and the ligand, we call it as the coordination number of the complex. See, for example, here the coordination number of here copper and ammonia. Here you can see in this case there are two molecules of ammonia attached to copper. It means 2 is its coordination number. Here 4 molecules of ammonia are giving away its pair of electrons to copper. It means 4 is its coordination number. Like this, the number of substrate molecules involved to form a coordinate bond with the substrate, that we call it as the coordination number. Is this thing clear? Now, ammonia has a single basic group capable of bonding to a metal ion, and hence it is unidentate ligand. That is, ammonia, it is having a single basic group NH3. It means 2 molecules of ammonia, 2 molecules of ammonia are required in this case to fill or uh, to saturate the vacant spaces of this copper metal ion. It means ammonia has a single basic group, or a single pair of electrons can be donated by ammonia, and that we call it as a unidentate ligand. Unidentate. Whereas ethylene diamine, it has accessible basic binding sites and it is bidentate. It can give away 2 pair of electrons, that is bidentate. Like that, thus ligands which are having more than one binding site, they are called as multidentate ligands. The substances, that is the organic molecule or the inorganic molecule or any ion, if it is having more than one binding site, such molecules or such ligand, we call them as a multidentate ligand. Example, EDTA, ethylene diamine. Students, just a second, be online. I have to send the link for resession. Just a second. Okay, thank you. So here, any ligand which is having more than one binding site, we call it as multidentate ligand, and the very most common and most widely used multidentate ligand is this EDTA. And here it has a hexadentate, that is, it can pair up with 6 binding sites. And it can also have a coordination number of 4 or 5. Okay, so that is about ligand and coordination number. Unidentate ligands such as ammonia, bidentate ligands such as ethylene diamine, multidentate ligand. Even ethylene diamine comes under multidentate definitely. Here you can see the definition. More than one binding site. Ethylene diamine has 2 binding sites, isn't it? So even ethylene diamine becomes multidentate ligand. Now, if a metal ion binds with a multidentate ligand, it means the ligand which is having 2 or more binding sites, it usually forms with the ligand a cyclic complex. Now you could have seen earlier, it forms a cyclic complex. Such complex we call it as chelate. Chelate, this you can expect it for 2 marks. The definition of chelate with example. Chelate is the complex where it consists of a metal ion which binds with a multidentate ligand and forms a cyclic complex. Just three three terminologies or three keywords. It has a metal ion binding with multidentate ligand and forming a cyclic complex that we call it as chelate. Okay. Now, there is another definition. So this was a 2-mark definition. There is another definition, that is, what is sequestering agent? A sequestering agent in the sense, if the ligand, if it forms a stable water soluble metal chelate, the same chelate, that is consisting of metal ion with ligand forming a cyclic complex. Moreover, if it is stable and if it is water soluble metal chelate, that we call it as a sequestering agent. The ligand which forms a, so here the ligand which forms a stable water soluble metal chelate, in the sense, this ligand will interact with the metal ion forming a coordinate bond and resulting in the formation of cyclic complex, that is chelate, which is soluble as well as stable, water soluble as well as stable. Such a ligand we call it as sequestering agent. See, keep in your mind, chelate means it is the complex, the cyclic complex. Sequestering agent means the ligand which will form a stable and water soluble chelate is nothing but a sequestering agent. Is this thing clear? So that is nothing but metal ion coordination complexes. Now next, we are having these organic molecular complexes. The second type of complexes, we call them as the organic molecular complexes. Here, as the title only indicates, organic, in the sense, here both the interactants are organic molecules here, and they may result from the non-covalent interaction between the substrate and the ligand. There we had M and L. Here both are organic molecules. Two or more organic molecules interact together, and their interaction is nothing but this non-covalent interaction. The bonding is non-covalent bonding between organic molecules, and such complexes we call them as organic molecular complexes. Okay. And here the non-covalent forces are due to various reasons. The non-covalent forces, it may be because of the electrostatic forces, it may be due to induction forces, or because of the polarization between an ion or a polar molecule and a non-polar molecule. See here, the non-covalent forces, it may be because of ion-ion interaction, ion dipole or dipole-dipole, or it may be because of ion-induced dipole and dipole-induced dipole, or it may also be because of the dispersion forces or London forces, what we call, that is induced dipole interaction. And here a molecular complex may be even a charge transfer complex, or it may be the donor acceptor complex. So definitely here there will be a donor which donates a pair of electrons and an acceptor which accepts a pair of electrons. Okay. Here, the bond resulting from the charge transfer, it may have some covalent character in addition to some non-covalent character. So, in brief, this is all about the organic molecular complexes. Fine. So, this is all about the introduction to complexation. Any doubts over here? Anyone has a doubt? Meanwhile, I'll just Anyone has a doubt? Fine. Anyone has a doubt? So the introduction to complex is clear to you all. Well, end the meeting and please join back so that we'll continue with the next most important topic of this chapter, that is the classification of complexes in detail. This was uh, just the classification based on the types of bonds involved. Whereas for 5 marks and 10 marks, they'll ask you the in detailed classification of complexes, which is very much important. So I'll end the meeting and please rejoin. Yeah, someone raised the hand. And here, had you seen the circular from principal sir? Sir has told that you'll have to name as per your register, RGHS register or maybe the college register. So name yourself in that way itself. Because when I take attendance, I'll give you the attendance only if your names are in that particular order. If you keep some nicknames or some other shortcut names and all, your attendance won't be considered, whoever it is. Right?